Good morning. All right, we're going to continue talking about Lewis structures today. Um, and we're going to now expand beyond just the Lewis structure itself. We're going to start talking about the shape of the molecules involved as well as their polarity. So let's start by looking at a couple of examples. Here we see that carbon has 4 bonds to hydrogen, right? To 4 different hydrogens. And in this molecule of methane, these bonds would be equivalent to each other, right? And we're going to see that we can consider, I'm going to do a couple more examples as well. We can consider a few things when looking at these. We can call all of these things, I'm going to do it on ammonia. These are what we call electron domains. And those are going to be either lone pairs or outer atoms. And we're going to see that electron domains, because they are made of electrons, either it's the electrons around another atom or it's the electrons of a lone pair. Remember that electrons are negatively charged, and we're going to see that they're going to repel each other. We're going to see that we have a theory to explain how the shapes of molecules can be predicted by understanding the idea that electron domains repel each other. And this is called valence shell electron EPR, electron pair repulsion, or VSEPR. Some people call it VSEPR, but that would be like switching them around. So VSEPR, maybe. It's a theory, which is going to suggest that electron pairs repel each other, whether those pairs are in lone pairs or they are within bonding pairs. They're going to repel other bonding domains, other electron domains. And we're going to see that, we kind of draw this, nice little methane molecule. Be like, aha, we have 90-degree angles here, right? And that's what it looks like on paper. But that's not really the best way to do it, because in fact, this is two-dimensional. And there's a better way to make them so they can be farther apart from each other. And we're going to actually start by looking at simpler or easier molecules to take a look at their shape first. Let's look at carbon dioxide. This is an easy shape for us. Carbon dioxide just has 2 electron domains on it, right? It has 2 oxygen atoms, and that's it. We're going to see that we have technically various ways to do this, right? We could do all sorts of weird. We could do all sorts of weird angles. But if we understand that oxygens, as the outer atoms of this molecule, would repel each other, we can see that this one on the top is going to be the best of all of those. We're going to see that this one will have bond angles of 180 degrees on either side. If we look at this one, we have a 90-degree angle, and I don't even know here, 30 degrees? Like, completely absurd. If they repel each other, there's no reason they would be close to each other at all. And in fact, we're going to see that everything will try and get as far away from each other as possible. And so, if we only have 2 electron domains, the best way to put them as far from each other as possible is 180 degrees. That's as far as they can go. If you try and make it 181, on the other side it becomes 179. so they're a little bit closer. So 180 is the maximum angle they can have away from each other. And we call this shape, surprisingly, linear. Right? They are all in a line. So these ones down here would be no good. Miss Bailey is getting up. You want to come over here? You want to go in my lap? Okay. All right. So, linear. That's going to be for just 2 electron domains. We're going to have we're going to assemble a chart at the end for this, but I want to also bring into play here a categorizing system where we can categorize molecules, and later on we're going to see that everything that falls into a certain category, we can have its shape be pretty easy for us. We're going to see that methane will fall under the AX4 category, and CO2 will fall under AX2. A represents the central atom, and for us that's always just one thing. We just have one central atom. We're going to see X will represent the number of outer atoms attached to A, not attracted, attached to your central atom. And E, although we don't have any with E yet, we're going to see it's the number of lone pairs on your central atom. All right, so everything is about the central atom. We don't care about the lone pairs on oxygen. We see that this molecule, CO2, has a carbon, and it's got 2 oxygens, AX2. It does not matter that the oxygens are double bonded. No impact. We're looking at the number of outer atoms. There are 2. There are no lone pairs on carbon, and so this molecule can be classified as AX2. Methane, on the other hand, we see here we have 4 outer atoms, and no lone pairs on carbon, and so we will call this under the category of AX4. If we go up a little bit, let's look at this water molecule. Of course, we have A for the oxygen. Number of outer atoms, we've got 2 of those. Number of lone pairs on the central atom, we have 2 of those. We're going to see that this one would be classified AX2E2 to signify that it's got on its central atom 2 outer atoms and 2 lone pairs. The ammonia here would be AX3E. Got 3 outer atoms, 1 lone pair. All right, again, only pay attention to stuff on the central atom, and again, double, triple bonds don't matter. We're only looking at number of atoms here. Okay, let's do one more. Yeah. Bad example because here, let's do a different one. Let's do this one. This cyanide. If carbon is the central atom, usually your least electronegative will be the central atom, by the way. I'll write that here. If we consider that, we have A, X, E only. 1 outer atom, 1 lone pair on carbon. That's it. Okay, sweetheart. HCl. Cl is the central atom. Hydrogen and fluorine can never be central atoms because they can only make 1 bond. We're going to see that this one would be AXE3. So just look at your central atom and see what it has on it. So doesn't matter number of bonds. If your Lewis structure is correctly drawn, you'll be able to categorize it correctly. You'll indicate A for everything. You'll have X for the number of outer atoms, and you'll have E for the number of lone pairs. All right, put your down there. Great, we have a categorizing system. We're going to see that anything that falls under AX2 will always be linear, but let's make that chart later. Let's look at another example. Let's look at boron tetrafluoride. If you're watching this later, it might be a good idea to pause it and then come up with the Lewis structure as practice. But for these, I'm going to go ahead and just keep doing them. So the Lewis structure for BF3, you might draw it like this, right? Remember that boron is happy just having 6 electrons. So with this, we're going to see we have, this could be classified as AX3, right? We have our central atom, the boron, 3 fluorines around it, and no lone pairs. Remember, it has 6 electrons only, doesn't have a full octet. So we're going to see that this molecule, if we move our angles like so, if we draw them like this, well, we have 180 here, but we have 90 degrees here. And there's no reason that one FBF angle should be larger than another, right? So doesn't really make sense. And then on the other side, we have 2 90-degree angles. And those are not going to be good. They're going to want to repel each other. They're going to all repel each other equally. And so, as a result, we're going to see that the real shape of this thing will actually form a triangle. Where now we have 120 degrees between all of them. They're all symmetrical. So all of these will have an angle of 120 degrees. And we call this shape trigonal planar. It's flat. It's within the plane. So within the plane of the tablet or paper or whatever, or the board. It's all in the same plane, and it forms a triangle. So we call it trigonal planar. We're going to see there are other ones that are trigonal. So unfortunately, we do need to put both. So anything that's going to follow the AX3 pattern will be trigonal planar in terms of its shape. And now let's take a look at that methane. So remember we saw before the methane categorized as AX4. We thought, okay, well, everything's got to be 90 degrees, right? But this is 2-dimensional. And if we actually go ahead and bring this into 3-dimensional space, and if you are a fan of balloons, you can do this yourself. It's pretty interesting. If you take 4 balloons, inflate them, tie them all together, they are going to form. Actually, interesting enough, if you put 2 balloons together, they're going to form a linear shape. If you put 3 balloons together, they're going to form a trigonal planar shape. And if you do 4 balloons, you're going to see that they will adopt what's called a tetrahedral shape. And I'm going to show you some pictures on Google because I'm terrible at drawing these. But essentially, this is the shape that we're going to see, where we are going to push this now into 3 dimensions. So this is going to be what's called a wedge, and that means it's coming out at you. It's towards you. So it's coming out of the plane of your paper or tablet or whatever, and it's coming out of the board. And on the other side, we call this thing a dash, and it is going away from you. It's going into the board. So if we want to think about what this looks like, here we go. All right, so here's what a tetrahedron looks like. So we have 2 bonds, or outer domains, that are going to be at angles to each other. These are the hydrogen on the top and on the right. And the other 2, I'm going to draw them, are down here. So one of them is coming towards you. I'm going to move slightly so you can see the other one. The other one is going away from you. So we have 2 of them, and then the other 2. So hopefully you can see that kind of represents kind of a pyramid shape, which is called a tetrahedron. And let's go ahead and pop over to Google real quick so we can look at some examples. Okay, so if we are, let me switch the window over because I always forget. Yeah. Okay, because 3D things are always better on Google. All of these have tetrahedral geometries. This is actually probably a pretty good one here. So we see that we have kind of two of them in the same plane, and then we have one coming out at you, one going away from you. And they form this kind of pyramid shape called a tetrahedron. And so this geometry, because this is now the best way that four things can get away from each other, we in fact have the bond angle right here. We're going to see it as 109.5. So that's what a tetrahedron looks like. And so we represent that in two dimensions by using wedges and dashes. Wedges mean that something is coming out of the plane towards you, the viewer, and a hydrogen is going into the plane, so away from you. So remember, this is kind of a pyramid shape, so it's called a tetrahedron. The bond angles here are all 109.5 degrees. And so that's better than 90, right? We can get them farther away from each other. The bigger the angle, the farther they are from each other. And we're going to see that all of these, so I'm only drawing one angle, but all of these angles are the same. Same with the other one, all the angles were 120 for the trigonal planar, and everything is 180 for linear. So we're going to see that all of these work out. What if we have five things? Well, let's take a look. What about the AX5 series? Well, if we look at that, we're going to see something like PCl5. Do your Lewis structure, pause the video. All right, we're doing it. So phosphorus pentachloride looks like this hypervalent species. Technically, we've got lone pairs on all these pesky chlorines, and I will be a good chemist and draw them all on. So this fits under the AX5 category, right? One central atom, five outer atoms. We're going to see that the best way to arrange these is actually now going to have different angles between them. There's going to be only one way to do this nicely, and we're going to see that they'll have three of them, three of our chlorines kind of all in the same plane as each other. And then we're going to also have a wedge and a dash. And if you want to think of it, it's kind of linear and trigonal planar at the same time. We're going to see the angle between these three, that's going to be 120 degrees. But between the top and the side ones, that's 90 degrees. And so we're going to see that we have two different bond angles here. So we call these, by the way, axial, the ones on the axes up and down. And we have these ones equatorial on the equator. So we have the equatorial angle for this shape is 120 degrees. And the axial angle, so the angle between the axial one and the equatorial one is 90 degrees. Between both axials, it's 120, right? And then between two equatorial ones, it's 120. Did I say 120 for both axial? It's 180. From the up chlorine to the down chlorine, 180. But we don't need to worry about that. So those are the two angles that we have here between things. And this is the best way to arrange them. So if you are somehow able to tie five balloons together, you're going to get this shape, which is called, by the way, Trigonal Pyramidal. So it's two triangular pyramids on top of each other. And again, we're going to go to Google to actually see the 3D so we can see what it really looks like, because my 3D drawings are not so great. And why bother when we have the unlimited power of the internet at our disposal? So let's take a look at Trigonal Pyramidal. Yeah. So let's see if if we can see these pyramids here. I mean, well, here's the like shape. So you see one up, one down, three in a triangle around each other. Here we kind of have, yeah, this is kind of the idea. So you've got a pyramid on top and a pyramid on bottom, and so that's kind of the where this name comes from. So and again here you have the angles are 90 degrees between your axial and equatorial position. And then between equatorials, you have 120 degrees. So that will be AX5. We have one more to talk about, which is very similar. AX6 would be something like sulfur hexafluoride. Go ahead and do its Lewis structure. And I'm going to go ahead and just do it with the geometry. So we're going to see that this one, load pairs. This one will look very similar to the trigonal pyramidal. But instead, we now have four-sided pyramids. And we're going to see that now we've just added a third one, or a fourth one, into our kind of equatorial place. And we're going to see now all of these angles are 90 degrees to each other. All these angles are 90 degrees. And this shape is going to be called octahedral. The reason it's called that is because it has 8 faces. It's essentially two pyramids, again, but they're four-sided pyramids. So two four-sided pyramids is 8 total sides, which is the octahedral shape. And we're going to go ahead and take a look at that. Let me go ahead and switch over here. So an octahedral shape, it's kind of got this square in the middle, and then one up, one down, and we have essentially two pyramids again put on top of each other, but in this case they're four-sided pyramids. And in fact, this one's kind of cool. You can see all of them at once. So trigonal planar here. We haven't talked about this one yet. Tetrahedral, trigonal bipyramidal, and then octahedral. So we have all these different shapes to worry about. And don't worry, we are going to make this, we're going to come up with a nice chart just like this that's going to get you to see all these lovely shapes. So far we've done this basic geometry column here. We're going to then talk about all these extra fun bits in a little bit. All right, so that's where we have it for now. So we're going to see that that's going to be our main idea. So I would suggest you go back to your previous homework on Lewis structures and assign bond angles to all of them and come up with the geometry for these. We're going to see that all the stuff we've talked about here, these are basic shapes. We have some more advanced shapes that we're going to talk about as well. So I would definitely suggest doing that. You're going to have more homework today or this week on doing these, but it's still a good idea to assign shapes to your previous ones. So those are our basic shapes. We're going to see that if we go ahead and do all these, we're going to see that this was linear. This trigonal planar. This one is tetrahedral. AX5 is trigonal bipyramidal. And then octahedral. We're going to see that the angles for all these are something you should also know. Don't forget trigonal bipyramidal has two sets of angles. And then we have an example for all of these. This would be carbon dioxide. Something is AX3, we did BF3, AX4, AX5, and AX6. We have examples of all these things. So when in doubt, if you forget a shape, which is unlikely because you're probably going to print out the table and use that, but if you ever do, if you kind of commit your examples to memory, it'll help you to remember all of these things. So, good stuff. Notice we have somewhat omitted all the cases with lone pairs. So we've been a little bit incomplete in our exploration of shapes. We're going to see that all of these are what we call electron geometries, because they are the shape of all electron domains within your ion or molecule. We're going to see that these electron geometries include all electron domains in the shape. But we're going to see that it's the best way to explain this. Because we cannot see lone pairs, it is helpful to also use molecular geometry. And we're going to see what those look like in a second. We're going to see that the shapes of these things are actually going to be different when we have lone pairs on our atoms. And the reason that it's necessary, even though we can't see lone pairs, the molecular geometry kind of includes only outer atoms, but takes into account the repulsion generated by the lone pair. And we'll just take a look at that in a second. And it may be easiest for us to take a look at water, for example. And we're going to see anytime you have a lone pair, you're going to have a different molecular geometry than your electron geometry. If we look at water, here, if we consider water, its category is AX2E2, right? And if we consider the total number of domains, the total domains which would be both your outer atoms and your lone pairs. In this case, is 4 for water. We have 2 lone pairs, 2 outer atoms. That's 4 total things stuck on our water molecule. We call this, by the way, a coordination number, which is the total number of domains, electron domains on your molecule. So we're going to see that it has a coordination number of 4. If we consider methane, CH4, categorized as AX4, also had a coordination number of 4, we're going to see that electronically speaking, the electron geometry is going to be tetrahedral for water. And so, really, it might be better for us to instead draw it like this. Let's maybe draw it like this. I usually put my wedge here, so I'll be consistent. So we have our wedge and our dash. I'm going to make the dash a little bit more obvious. So we have 4 things on them, and we're going to expect a bond angle of 109.5. But we're going to see that we have a couple of things to consider here. First off, a lone pair is stronger at repelling things than atoms are. Atoms are much larger, so their electrons are more spread out. Lone pairs are fairly concentrated. We're going to see that lone pairs, they repel more strongly than atoms do. And so in reality, they actually push a little bit more on our little hydrogens. And they compress that angle to 104.9 degrees. So we actually get a smaller angle between the HOH atoms, because the lone pairs actually are repelling the hydrogens more than the hydrogens repel each other. So the lone pairs are pushing the hydrogens closer together even though they don't want to be, because lone pairs are stronger at repelling because they're more concentrated electron density. So as a result, we end up getting a smaller bond angle because we have lone pairs, and we're going to see this trend will always continue. Anytime we have a lone pair in a molecule, it's going to make our bond angles less than we would expect. And secondly, because we can't see them, and again, I use the word see in quotes, we can't really see atoms either. We can kind of. There's some pretty cool electron micrographs of some pretty small things. We can see kind of the effects of atoms. But atoms are much, 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 much larger than electrons are, right? So we don't really see them. And so we describe the shape as if they weren't there. And so if we just kind of hide them, this is what we're ending up with. This is kind of the leftovers. If we pretend those lone pairs aren't there, we still have our 104.9 degree angle. We're going to continue to apply their effects, but we're going to also consider that we can't see them. And so the shape for this thing, we only consider the atoms. So we look at what shape the atoms look like. And we describe this shape as bent. You know, you might expect it to be linear, right? But it's not, because we have a bond angle of 104.9. So the lone pairs still have an effect on the shape, but if we look at what shape the atoms make a bent shape. The atoms themselves do not make a tetrahedral shape, though if we include the lone pairs in that shape, that would be tetrahedral. So we use this molecular geometry to distinguish atoms only versus atoms and lone pairs. Atoms and lone pairs is electron geometry. Atoms alone is molecular geometry. As soon as you have a lone pair on your central atom, all it takes is one, your molecular geometry will be different from your electron geometry. For CH4, they're the same. Its electron geometry is tetrahedral. Its molecular geometry is tetrahedral. And because that's AX4, there's no lone pairs there. For water, AX2E2, and we're going to see anything that has AX2E2 will be bent and will have bond angles of roughly 104.9. The electron geometry here is tetrahedral. Anything with a coordination number of 4 will have an electron geometry that's tetrahedral. And its molecular geometry is bent. So because there are lone pairs in the molecule on the central atom, its molecular geometry is different from the electron geometry. All right, and so we'll take a look at that one on Google in a little bit, but I want to do ammonia first. If we consider ammonia, that falls under the category of AX3E. Coordination number X plus E, 3 plus 1, 4. So still electron geometry is tetrahedral here. But let's take a look at what the shape of this is going to be. I'm going to go down a little bit just so we have some more space because I want to also do HCl. So we'll keep that as well. So, NH3. If we go ahead and draw this, which I should have, in 3D, or as best we can approximate 3D, we're going to see that the angles here, again, are going to be a little bit less. These ones are about 107 degrees. So still less than 109.5 pure tetrahedral, but not as far gone as the bent angle of 104.9. So we're a little bit less in between because we only have one lone pair. And if we kind of pretend that the lone pair isn't there, we get this shape, which is a pyramid, a single pyramid. Oh, that's terrible. Let's try. Oh no, I've lost my. Okay, let's pretend I never drew anything. We'll look at it on Google. This shape is called Trigonal Pyramidal. So not bipyramidal, only one pyramid. So it's just one pyramid. That's what it looks like. So we call this trigonal pyramidal. All right, so let's go ahead and take a look at these bent and trigonal pyramidal geometries here. So lovely. Oh my God, look at these lone pairs that just all in a line. We see here that indeed its electron geometry is tetrahedral. And if we pretend that those lone pairs aren't there, we are left with just this, with its bond angle of 104.9. I don't know where they're getting this 104.4. That's lies. It's 104.9. But suffice it to say, your geometry here is bent. All right, and so we're going to see here that as a result, the shape of this looks like this. That's what we see. We see a bent shape. We might expect it to be linear, but it's not. It's bent. So they force the the lone pairs, although we cannot see them, force these two hydrogens to be at a different angle. So they're not 180 degrees apart, they're 104 degrees apart. All right? Trigonal Pyramidal. Let's look at ammonia. Same thing here. So we have our tetrahedral electron geometry. We now pretend the lone pair isn't here, and we're left with a pyramid. And so we see that bond angle of about 107. So this is what it looks like. They're all pointing down a little bit. So it's not trigonal planar. Trigonal planar, everything's in a plane. However, these are in a pyramid. They're pushed down. So the bond angles are 107, not 120. So we're seeing a different bond angle there. So we're looking at trigonal pyramidal shape there. All right, then HCl is kind of an easy one. That's AXE3. Its electron geometry is tetrahedral, and its molecular geometry is linear. And how do we know that? Because there's really only two atoms, so there's no angle to really compare with. So the hydrogen's already as far away from everything as it can be. So we still would say it's about 180 degrees, even though there's not really an angle here. So we just call it linear, right? There's no like some weird bonkers thing like that, right? It's two things, 2 points. All you can do is make a line with them. All right. If you had more points, you could make a bent shape or a trigonal pyramid. So this is our 4 electron domain category. So everything that is tetrahedral electronically will be one of these 3. So AX4, AX3E, AX2E2, AXE3, all of those are tetrahedral electron geometry. And if we take a look at the rest, they would all have different molecular geometries. All right, so we can go into the rest. We'll take a look at the coordination number of 3. That would be AX3 or AX2E or AXE2, which that's not really a common one, but the first 2 we have a couple of examples of. I don't think I can think of any off the top of my head that are AXE2, but they would still be a coordination number of 3. The electron geometry for these is trigonal planar. For example, AX3, we have SO3. (120-degree angles). But if we take a look at something like nitrite, do its Lewis structure, pause the video. All right, here we go. This would be our Lewis structure with a formal charge on the oxygen. We see here we have 2 outer atoms and a lone pair on nitrogen. So this one is AX2E. And if we're going to pretend, so we're looking at somewhat less than 120-degree bond angle here. I should do that on the other side. Because the lone pair is going to push the oxygens away from itself. It's going to push them a little bit down, so a little bit less than 120. And that's really as far as we take it. We don't say 117, we don't say 118.4, whatever, just less than 120. And we're going to see that if we pretend the lone pair isn't there, we see that this one is also going to be a bent shape. So it looks similar to water, right? We have two things pointing down a little bit. And while the angle is different from water, the shape is still called bent. All right, and for this one, it's just trigonal planar. So, easy. If we did have something that was AX2 or AXE2, that would fall under the category of linear as well. Only one outer atom, uh, so it's going to be a linear thing. But I can't think of anything that would fall under this category. All right, let's just Google it. Let's see what we get. Let's take a look. AXE2. Yeah, let's see what we get here. Is anything going to fall under this shape? AXE2. Oh, O2 does. That's curious. I hadn't considered that. Yeah. Perfect. There we go. We have O2, for example. Aha, indeed, this oxygen has one outer atom and two lone pairs. We can look at either one as the central atom. And so indeed we see it's linear, right? No real, it's just 2 points, so there we go. So oxygen would fit this category. Cool. So that's coordination number of 3. By the way, I have a handy chart for all this stuff, so it will be nicely consolidated for you. Let's look at AX5 category things. So, or coordination number 5. So we're going to have AX4E, AX3E2, AX2E3, and I can't think of anything that would fall under this category, but again, I have been proven wrong before. So, if we look at all these would be trigonal bipyramidal or electron geometry. For molecular geometry, we see we're going to take one thing off. So this would be, for example, would this work? How many lone pairs? No, that would have 2 lone pairs still. Yeah, SF4 would fit this category. Okay, so in this case, we have sulfur with 4 fluorines. I'm going to not... Fine, I'll draw this. We're going to see, in the case of having one lone pair, and in fact, I'm going to move all these ones down. Move them out of the way for now. The lone pair must go in an equatorial position. Because it's going to be able to push things away from itself better in that sort of shape. So, because if you have it at 90 degrees, it wants to push everything away from it. You're going to end up crowding your fluorines all the way down there. So, we're going to see that this shape is called seesaw. And let's take a look at what that looks like in 3D, because again, I'm not the best at drawing these things. And let's see, seesaw, yeah. Oh, I don't need the angles, but this is the idea. So it looks like a seesaw. So you have your sulfur, your 4 fluorides, and the lone pair is on the other side. And again, we pretend it's not there. Here we go. So we see that it kind of, the lone pair pushes things around, and we end up with a seesaw, like the thing that children play on, right? And so there's your angles technically if you really wanted, as far as we trust these, 86.5102, so a little bit less, right? Because the lone pair will push them down further. So that's the idea here. So that's what it looks like. It looks like a seesaw. So it's got two legs down and then the linear part. Right? If we have AX2E2, I think what would satisfy these ones? Three things. So maybe CLF3? Yeah, that would probably work. Yeah, that'll work. So if we take a look at this Lewis structure, go ahead and do it, as always. If we pretend these lone pairs aren't there, we're going to see that this is a T-shaped molecule. So we're going to see that it would just look like this. And so our bond angles are just 90 degrees, again, here. So this is called T-shape geometry. All right, AX2E2, or E3, sorry. This would be something like XE, I think Xenon Tetrafluoride would do this. Yeah, that would work. All right, we're going to get rid of this. All right, XEF2, we're going to see that we're going to end up with our three lone pairs, and this will just be linear. If we're looking at the F to F, the FXEF bond is 180 degrees, right? That's linear. That's a bond angle that's linear. So the lone pairs will go in the equatorial positions, and they're pushing things away equally, so you end up with a completely linear molecule up on the top there. All right, and so that's going to be the best way to put all these lone pairs in there. All right, one more to go, and then we can talk about hybridization, and that's all I want to do today. Let's look at coordination number of 6. So, if we have a coordination number of 6, this is octahedral to begin with. We saw that something like SF6 would fall under our kind of main electron geometry, no lone pairs. But we see we can transform all these. So something with 5 atoms and 1 lone pair, this would be CLF5, for example. Do your geometry. Does not really matter where we put the lone pair because everything was 90 degrees. And so we're going to end up just choosing where to put it. And as a result, if we pretend it's not there, we end up with a shape that is square pyramidal. And let's take a look at what that looks like. So it's going to form a square pyramid. And so I've drawn my lone pair on the bottom, but suffice it to say, we end up with the, I put mine on the top, but this one we have it on the sides here. So this is a square pyramid. You can also technically get this with a coordination number of 5, but that's going to be for special cases of transition metals, so we're not going to really worry about that for us right now. So if you can see here, we have the 4 of them in the plane, and then one up that forms a pyramid. We have our lone pair down there. And so that's going to be our shape. All right, a square pyramid. If we've got 2 lone pairs, AX4E2, example for that Xenon Tetrafluoride, we're going to put the lone pairs on opposite sides from each other. It does not matter which sides because this thing is symmetrical. I put them top and bottom. What's left is we have a square planar shape. Everything is in a square. Fluorine, 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 square. So everything is in the plane. It's all 90-degree angles to each other. All right, if we keep going, AX3E3, what would be this one? Let's see. Something with 3 outer atoms and 3 lone pairs. Let's Google it. I can't think of an example. AX3E3. What would be an example for this? I can't really think of anything that would fit this category. Well, no wonder. There aren't any. So, go figure. So there aren't any, but it would be T-shape, yeah. That's what I was going for. But as you can see here, these ones that have even more just don't exist. So we have octahedral, square pyramid, square planar. These ones don't really exist, but they would be T-shaped and linear if we were to continue. So that's quite a lot we've done, right? Let's hop over to Discord real quick so we can see that we have a handy chart for us. Okay, so in our extra resources, look what we have. A chart, and it's got all this fun stuff. So we have the coordination number on the left axis. We have the number of lone pairs on the right, and all these shapes. Here they write angled. We call these bent, but yeah, that's the idea. So we've got all these different shapes here, and there's examples of all of them. So I'm going to go ahead and copy this again. So we have that for us again there. So just remember, angled is bent. So that's what we're looking at here. Okay, so let's go ahead and go back here. But we don't have an example for that. So the point of all this stuff is it's going to allow us to evaluate things in 3 dimensions. We're going to be able to determine the polarity of an overall molecule by examining its shape. We can determine its polarity. So let's take a look. And in fact, I'm going to start with an easier example. We'll start with CO2. if we want to evaluate what type of bond is a CO bond, we would look at their electronegativities and we would subtract them. We'd say, 3.5, 2.4, 2.5. Yeah, 2.5. The difference of electronegativity is 1 polar covalent, right? Smack dab in the middle of the polar covalent range. So that tells us that we have partial negatives on the oxygens and partial positives on the carbon. Have I shown these dipole arrows before? These arrows are special. They show the positive side that has a little plus on it on the arrow, and then the arrowhead is the negative side. And we're going to see that on the other oxygen, it will be the same. We have the plus side on the carbon, then minus side on the oxygen. And we're going to see overall, those oxygens are going to be pulling equally on carbon. One is pulling the electrons to the right, the other one is pulling the electrons to the left. Each oxygen is identical, right? They would have equal affinity for these electrons, equal electronegativity. And so they're going to pull equally. And if they're pulling equally in opposite directions, nothing changes. And so overall, we're going to see that this molecule does not have a dipole because they've canceled out. So dipole plus and minus, partial positive, partial negative. We saw those with the polar bonds. Polar bonds are dipoles, positive pole, negative pole. But because they have canceled each other out, this is a non-polar molecule, even though the bonds are polar. And we're going to see it's the same case for CF4. All of those are polar bonds, but they all cancel each other out. They're all pulling it equally in different directions, and those all cancel out. We're going to see something like this, though. Carbon monoxide. It will indeed be polar because nothing to cancel this dipole out. So this molecule is polar. The dipole is not canceled out. And here's the super easy way to tell if a molecule is polar or not. How to tell if it's polar. Here we go. If any electron domains are non-identical, it's polar. That's it. That's as easy as it is. If you have any two electron domains on your central atom that are not identical to each other, you'll have a polar molecule. Here's an example. And the left molecule, they're all identical. They're all hydrogens. So, nonpolar molecule. Done. We have a chlorine, and chlorine is not the same thing as a hydrogen, therefore it's polar. Easy. Let's ask yourself, is everything identical? If so, polar. No, sorry. If everything is identical, non-polar. If anything is not identical, it is polar. Here's another example. We have to ask ourselves, is a hydrogen the same thing as a lone pair? No. Clearly then polar. A lone pair is not the same thing as an atom. So anything that has a lone pair should be polar as well. So we're going to see that we have polarity all over the place. Anytime you have any electron domains that are different from each other, you're going to have a polar molecule. Right? So that's the idea here. It's really easy to tell. And we're going to explore this more in, I think, in 2 chapters. I think we do gases next, and then we talk about intermolecular forces. The idea of polarity is going to be more important then. So, but that's all it takes. That's the check. That's our litmus test. Do we have any 2 non-identical electron domains on our central atom? If we have anything that doesn't exactly equal something else, it shall be polar. And if you want to go really physics crazy about it, you could draw all your dipole vectors and see that they don't cancel out if you have things that are not equal to each other. So we're going to see that most things will be polar. But how polar they are is a different matter. So that will depend on bond polarity and everything else. So we'll worry about that later. All right. So that is polarity. Easy enough. And the reason that it's important that we have these things is we're going to see that that's going to affect the properties of these molecules. So we'll get to that again in 2 chapters. Cool. Then let's go ahead and look at the last little bit here. Hybridization theory. This is something much very, very relevant in organic chemistry specifically, but it's going to help explain some of the phenomena we see with Lewis structures. So if we are going to consider the molecule methane, and have I talked about how bonds are made? All right, let's take a step back here. Oh no, I can do it now. Okay, so consider that bonds are made when orbitals overlap with each other. And we're going to see something like H2, hydrogen gas. They just have s orbitals. We're going to see that that overlap there is the bond between the two. And so we're going to see that when s orbitals overlap, they form a sigma bond. When s orbitals overlap. And we're going to see that when p orbitals overlap, let's take a look at something like this. When p orbitals overlap, they don't really overlap as nicely. When p orbitals overlap, they kind of bend their lobes towards each other. I'm going to show you it on Google because I'm a terrible artist for this sort of thing. That's what's called a pi bond. And that's when 2p orbitals overlap. And we're going to see, let's take Let's take a second to go on Google here. My God, we could even go to orbital Messi. How fun. Okay. Well, these are kind of, there we go. This is what I'm looking for. So with these sort of things, a p or a pi bond is formed when p orbitals overlap. Those are the ones that are dumbbell shaped. And so when they overlap, they make a pi bond. When sigma orbitals overlap, they make sigma bonds. Right? That's the idea here. And we can take a look at some of these things in methane. If we think about methane, this is carbon's electron configuration, right? If we were to just use these electrons as is, if we were to bond them with hydrogen, well, we're going to say, well, we have the 2s orbital bonding with the 1s orbital of hydrogen. And again, we have a second one that does that. And then we have the p orbital that bonds with the s orbital to make other ones. But s and p are different energies. And they're different shapes, right? There are different energies and different shapes. These are mathematical models, right? They're probability distributions. And we're going to see that because they are different energies and different shapes, we would expect CH4 to have two different types of bonds. We would expect, okay, well, we've got carbon's s orbital. We would expect that to overlap with some s orbitals. And then we've got p orbitals that are going to overlap with s orbitals. This might be what we would expect methane to look like. And I'm only showing one half of the p orbital because it's going to get messy. Sorry, that's the s as well. These are the hydrogens, and this is the carbon in the middle. Okay, let's just undo that. That's our carbon. We would expect, well, now we have two giant bonds and two small bonds, right? But experimentally, all four bonds are equivalent. So the bond length, the bond strength, everything is identical with these bonds. Otherwise, we might see some polarity here. And we know methane is completely nonpolar. Because if we'd have different things on our carbon, we would expect different properties. But all four bonds are, in fact, equivalent to each other. And so hybridization theory says, well, we're not really going to have these electrons in different orbitals. What we're going to do is we're going to hybridize them. So carbon will, in fact, if we take a look at the kind of energy-wise, let's put the p orbital up here. If we take a look at the energy, 2s energy, electrons are lower energy than 2p electrons are. So what it's going to do is it's going to sacrifice some of the stability, the lower energy of the 2s, to bring the 2p orbitals lower in energy. They're going to hybridize. We're going to combine the s orbitals and the 3p orbitals to make sp3 orbitals. And we're going to see that we had two electrons from p, two electrons from s. We're going to hybridize all of them to make 4 sp3 hybrid orbitals. And so now we have 4 electrons that are all equal in energy to each other. And now, we can go ahead and make it so that these bonds are equivalent because they're all using the same orbitals now. And sp3 orbitals look like this. It is made of a combination of the s orbital and 3 p orbitals. Remember, p orbitals are xyz oriented. And we're going to see that as a result, we're going to have hybrids that are kind of look like cartoon exclamation points, I suppose. And those, when they overlap with s orbitals, form sigma bonds. And sigma bonds are what we know as single bonds. So we're going to see that an sp3 orbital and an s orbital, so carbon and hydrogen, this will be a sigma bond in between them. We say that because a sigma bond is defined by having direct overlap, whereas the pi orbitals had that kind of partial overlap. If you remember my lovely drawing, they don't really overlap directly. They overlap kind of on their sides a little bit. So sigma bonds are formed between these hybrid orbitals and just the s orbitals of the hydrogen. And so sigma bonds are going to be our single bonds, and these are direct orbital overlap. Whereas pi bonds, those are going to be your double and triple bonds, and those are partial overlap. As you can imagine, if you have direct overlap, sigma bonds are going to be stronger than pi bonds will be. And we're going to see that we can correlate the coordination number with the hybridization that an atom will undergo. We're going to see that something like this, formaldehyde, trigonal planar, we have to consider here we have 3 sigma bonds and 1 pi bond. The pi bond will be our double bond, the additional bonds. We have a single bond to oxygen, that's the sigma bond, and then we have an additional bond, which is the pi bond. So those are going to be your extra bonds, will be pi bonds. Pi bonds have to be p orbitals only. And sigma bonds will be made of s orbitals or hybrid orbitals. And so we can see here we need 1 p orbital left on carbon to make that pi bond, but we also have to make 3 single bonds. So in this case, we're only going to hybridize 2 of the p orbitals. So we need 1 p orbital and so we're going to hybridize the s orbital and 2 p orbitals. Remember, we have 3 p orbitals normally. And we're going to make sp2 orbitals. We're going to make 3 of those. So really this carbon will have 3 electrons in sp2 orbitals and 1 electron in a p orbital. These ones are going to make the sigma bonds. And the p orbital there is going to be for the pi bond. And we're going to see that if we have 2 double bonds, don't worry, again, I'm going to show you an easy way to figure this out. we have a sigma bond in each one, and we have a pi bond in each one. So we need 2 p orbitals. And so we're going to have sp orbitals and then the other 2 p orbitals in terms of energy again. And so our hybrid in this case will be sp. And here's the easy way to tell. If you have a coordination number of 4, be AX4, AX3E, etc., you are sp3 hybrid. Anything that is AX4 is sp3 hybridized. Ammonia, water, methane, carbon tetrachloride, sulfate. All of these things are sp3 hybridized. Sulfate's a bad example. Let's not use sulfate. Ammonium. All of these things, sp3 hybridized. If your coordination number is 3, you're really sp2 hybridized. So just look at how many things you have attached to your atom of interest. If you have 4 things on it, 2 lone pairs, 2 atoms, whatever, those 4 things happen to be, you have sp3 hybrids. If you have only 3 things attached, you are sp2 hybridized. And then if you have a coordination number of 2, like carbon dioxide, you are sp hybridized. And we could also think of these things in shape. They're all correlated together. These are tetrahedral things. Electron geometry. These are all trigonal planar. And of course we have the linear. And again, we're looking at a base angle of 109.5, base angle of 120, base angle of 180. These might be less depending on your molecular geometry, but that's the idea here. So all these things are related. So your hybridization of your orbitals allows us to make multiple bonds that have equal energy to each other. So we can make 4 bonds with carbon to each of 4 hydrogens. And all those will be equal in energy because they are hybrid orbitals. They're not made of s orbitals and p orbitals, but they're made of a hybrid of those, sp3 orbitals, that are involved in making those bonds. And then for trigonal planar stuff, you use sp2 orbitals, and then for the other ones we use sp orbitals. All right, so there we have it. We will continue on next time talking about how multiple bonds form, as well as looking at molecular orbitals. So these are atomic orbitals, and we're looking at kind of more simple examples. We're going to look at more complicated things on Thursday, yeah. So we'll get to that then. So, all right, awesome. See you guys next time.